The following short video will demonstrate how Kruskal's algorithm is applied to determine a minimum spanning tree. We'll engage briefly with the prior learning that students will have engaged with before experiencing this algorithm. We can represent many real-life problems using a graph. A graph is a finite set of dots and connecting links that can simplify real-life models. The dots are called vertices or nodes. The links are called edges or arcs. Sometimes weights are assigned to the edges. Weights could represent the distance, time taken, or cost of travel and so forth between two locations or two nodes. Paths, cycles, and trees play an important role in our learning of graph theory. A path is a sequence of connected vertices in a graph. This could just connect two vertices or multiple vertices. It doesn't have to connect all the vertices in the graph. In this case, we have a path highlighted between Monaco, Paris, Edinburgh, and Dublin. A cycle, on the other hand, is a path that starts and finishes at the same vertex. It's like a closed path. We can see the closed path nature, cycle nature, of the diagram on the right between Costa, McDonald's, and Garda Station. On the graph on the left, we have certain edges and vertices of the graph highlighted, and we refer to this as a tree. The diagram on the right also has certain edges and vertices highlighted, but this is not a tree. Can you remember why one is a tree and the other is not a tree? A tree is a connected graph with no cycles. A spanning tree is a connected graph that includes all of the vertices of the graph, but doesn't have to include all of the edges of the graph. By posing this question on the slide, we, the teachers, are demonstrating to the students the benefit to them to learn by discovery, thereby enabling them to progress, to deepen and apply their learning. We might present our students with diagrams as are shown here and ask them to interpret what they see or understand using their own language. We could then ask them to explain further what they understand by the term minimum spanning tree using the correct networks and graph terminology. We would hope they would say that the minimum spanning tree is a spanning tree where the total weight of all the selected edges is as small as possible. There are two mathematical methods, known as algorithms on our specification, to deal with calculating minimum spanning trees. Let's consider the following problem. The manager of a theme park wants to widen and resurface some of these paths so as to provide easier access for maintenance vehicles. The manager wishes to connect all parts of the theme park in a most cost-efficient way by minimizing the total lengths of paths selected to be widened and resurfaced. The manager is asked to calculate the minimum length path that must be resurfaced if each of the attractions and the shop are to be interconnected. While we present this problem in class, students may establish the need to create a minimum spanning tree. So using this opportunity in class, we introduce them to one of the two algorithms that deal with minimum spanning trees, Kruskal's algorithm. So let's have a look at that network again. The first step in this algorithm is to identify the edge of least weight in the network. We highlight both nodes that connect this edge. In this case, it's 32-meter edge joining nodes River Rapids and the Log Flume. We'll highlight them and add the edge to our minimum spanning tree. Our second step then asks us to select the next edge of least weight. Bearing in mind if there's a choice of equal edges, then either will do as long as it does not form a cycle with the edges already selected. And we'll add this edge to the minimum spanning tree and we'll highlight the appropriate nodes. We can see the 36-meter edge is the next smallest. We'll highlight the nodes in question and add that edge to our minimum spanning tree. We repeat the process until all the nodes have been highlighted. We'll pause at this point. We see there are two edges of weight 54 meters. We do not select the edge connecting Kitty Corner and the shop, as it would form a cycle. So we select the other edge of 54 meters connecting Animal Farm and the runaway train. We highlight those nodes and we'll add the edge to our minimum spanning tree. We continue with the process, selecting the next smallest edge, ensuring it does not form a cycle with the edges already selected. Now that we have all the nodes highlighted, we must make sure that all the nodes are connected. In other words, that the graph is not disconnected. We can see there seems to be 3 separate subgraphs connecting the nodes in this diagram. This is one here, second one over connecting these 3 nodes, and our third subgraph connecting these 2 nodes. So we repeat our second step and select the next smallest edge, ensuring it does not form a cycle with the edges already selected. The 64-meter edge connecting River Rapids and the pirate chip is added to the minimum spanning tree. Again, we see the tree is not connected. We're limited in our selection of edges, as many will form cycles. The next and final edge selected is the 75-meter edge connecting Animal Farm and the pirate ship. We add that to our minimum spanning tree. So if we remove the edges not used, we can take a look at the spanning tree formed. We can see that all the nodes are connected, so it is a spanning tree. And since we considered the smallest edge available each time, we are confident to say that we have created a minimum spanning tree. Let's remind ourselves again of all the steps in this algorithm, suitably framed at the top left of our screen. And finally, let's add up all the selected edges to answer our question. Remember, we were asked to calculate the minimum path length, so if we sum these edges selected, we see our minimum path length is 417 meters. Kruskal's algorithm is a greedy algorithm, which means that as the solution builds piece by piece, the lowest value is always chosen. I hope that you've enjoyed this short video. If you have any questions, then please feel free to send us an email at the email address listed, and please follow us on Twitter as well. Thank you.